Right, using the dot product, we can also figure out how to do projections. I discussed projection a little bit. So here's how projections work. If you have one vector u, another vector v, then you draw this perpendicular line to it, and this part right here is called the projection of u onto v. Now, different textbooks use slightly different notation for the projection. Some books would say this is just this length, and to actually get the vector that's like this, you would put a arrow on top to show that it's an actual vector. I just noticed that in our textbook, even without this arrow, it means the vector. Okay, so we're going to say projection is a vector. That's like that. And if I want the actual length, I will have to take the norm of this quantity. Okay? And then this here is called projection of u onto v, but the perpendicular component. So if you have the perpendicular component, it means this part here. So this is called a perpendicular projection. All right. Let's figure out the formula for it. First, I know that the magnitude of the projection is basically this length times the cosine of the angle between. So u times the length of u times the cosine of the angle between. There needs a little bit of warning here, because if angle theta is bigger than 90 degrees, then the right side will be negative, because cosine of the angle of an obtuse angle will be negative. So this is only true if the angle is less than 90. But this is just intermediate step. You're never going to be asked to do it this way. We just need the final formula. But rather than throwing you the formula and say, oh, you should memorize this, I think it's better for me to show you how it's derived. Okay. All right. So here's what I want to do. I'm going to multiply by v and divide it by v. It looks like I'm making things more complicated, but the top is now something that we recognize. What is this? Dot product. Right? Now sometimes this is called a scalar projection. It only deals with the length. Now we have to turn that into an actual vector. How how do you make a length into a vector? Well, you just need a unit vector in the direction of v and multiply by this length, right? Do you remember how we solved questions like find the vector in the direction of some... I wish I had the problem right next to me, but if you had a question like find a vector of magnitude 3 in direction of v, say 1, 2, 3. How do you solve such a question?
Multiplied by 3.
Yeah, but the problem is this doesn't have magnitude 1.
You have to take the 1 over the magnitude.
Right, you have to divide this by the magnitude of v to come up with the unit vector. So the solution of this cute problem is first you have to find the unit vector in the direction of v, and that's by definition you take the vector and divide it by its size.
Square root of 14.
Thank you. So this is square root of 14 because 1 squared plus 2 squared plus 3 squared, that's 14. Right? So square root of 14. And then since this has the magnitude 1 in the direction of v, now you multiply 3 to it, and that's the answer. So the answer is you multiply 3 to the v unit vector, and that's 3 comma 6 comma 9 over square root of 14. So that's how you solve such a question. Okay? Now this is very relevant to the formula that we have now, because this is the magnitude we want. What's the direction we want? We want the direction to be the same vector as v, right? I want the direction to be the same as this v. And therefore, to get the actual projection, we want u onto v as take v and divide it by the norm of v, so I get the unit vector in the direction of v, and multiply by the magnitude we want, which is this thing, u dot v over the norm of v. And therefore, see, this is a scalar, this is a scalar, that's a scalar, so they can be all multiplied together. V itself, this is the only vector that we have. So if I multiply this to this, I get v squared, and on top I have u dot v. So that's the projection. Okay? Does that make sense? So that's the formula. It's kind of hard to memorize, but if you think about it, it's not too bad. But this is what we call vector projection. Okay. Finally, for the perpendicular projection, we just use the Pythagorean theorem and that's it. So we're going to say projection perpendicular u onto v squared plus this length squared, which is u dot v squared is equal to the hypotenuse, which is u, norm of u squared. From here, we can get the formula that projection of u onto v perpendicular is square root of norm of u minus u dot v squared. So that's the formula that we get. And you know, honestly, I just derived it on the spot. I don't remember this formula. So if I have a question like this, I'll just use a Pythagorean theorem. It's not worth it to memorize it, because it's easy to derive. Okay, so let's summarize everything that we learned so far. Let's put a summary. What's the summary? Summary is that you have something called a dot product, which is norm times the norm times the cosine of the angle between. And in the context of coordinates, the dot product is just simply product of the components, and you add them up. And then this is the formula that I didn't write before, but if you take this formula and solve for cosine, we get the following thing. I divide this to the other side and take the cosine inverse. That gives you the angle between the two things. That if you want the angle between, what you need to do is take the cosine inverse of u dot v over u v. And then we also have projection of u onto v as u dot v over v squared, v, whose magnitude will just simply be the absolute value of this. I didn't have the absolute value over here because I didn't take into account where the angle is obtuse, but if the angle is obtuse, this will give you a negative value, whereas this is a magnitude, so the left side is always positive, so you need to put this absolute value. And then the perpendicular projection of u onto v is square root of u squared minus u dot v over v squared. So these are the formulas. In addition, there are a few properties that you have to know. The properties of the dot product number one is commutative. Number two, it satisfies the distributive property. Number three, if u and v are perpendicular, that means u dot v is 0. And if you do a dot product of any vector with itself, that means the angle is 0, so you end up with u, magnitude of u times magnitude of u, so that gives you u squared. And number 5, if you have any constant times uv, I use this property without really explaining why, but I don't think this requires much explanation. So multiplying a constant to one of the vectors and doing a dot product, you can move constants around. Scalars can be moved around. That's basically it. So these are all the properties that you have to know about the dot product. And if you know these, then you're good to go.